Welcome, everyone. Today, we're going to get hands-on with one of the most fundamental forces in the universe, gravity. But we're not just going to talk about it. Oh, no. We're actually going to measure it. And just a quick note before we dive in, this guide was put together especially for Professor Londoño's class. We really hope this helps you nail your lab work. So think about this. How do we actually measure the pull of gravity right where you're standing? I mean, really pin down a precise number. Well, that's exactly what we're here to do today. We are on a mission to find our very own local value for G. Okay, so here's our game plan. First, we'll talk about why we're even on this quest for G. Then we'll get to know the gear we'll be using. After that, it's showtime. We'll run the experiment. Then we'll figure out what all the data means. And finally, the big payoff, calculating your own G. So let's start with section 1. You might be wondering why go through all this trouble, right? Well, measuring G is a classic, a rite of passage in physics. It's how we prove a fundamental truth, that things in freefall speed up at a totally constant rate, all thanks to gravity. And here's something that's really cool. G isn't some fixed number that's the same everywhere. Nope. It actually changes a tiny bit depending on where you are on Earth. Take a look. Gravity's pull in Maryland is just a hair stronger than it is in Sydney, Australia. Our whole goal today is to find out what it is precisely for our location. You know, for the longest time, getting a good number for this was just incredibly hard. I mean, can you imagine trying to time a falling rock with an old-school stopwatch? It's over in a flash. So people came up with clever workarounds like the Atwood machine, just to slow things down. But lucky for us, we've got a much, much better way to do it now. So how do we get around those old problems? Let's move on and check out the modern tools that are going to let us capture that split-second fall with incredible precision. Okay, so our setup is actually pretty slick and simple. We've got 4 key players. The spark generator, that's our super precise clock. The lead mass, that's our falling object. A special paper strip, that's our data log. And an electromagnet, which gives us that perfect, clean start. But really, the star of the whole show is this spark generator. It's plugged into a normal wall socket, which provides alternating current at 60 Hertz. Now, what that means for us is that this thing can shoot out a tiny spark exactly 60 times every second. Every spark leaves a little mark on our paper, which means we have a timestamp every 60th of a second. It's an absolutely brilliant way to time something that falls so fast. All right, we've met the team. Now let's get into the action. This is your play-by-play for running the experiment and getting that perfect strip of data. First things first, you're going to attach the paper strip right up top to the electromagnet. Next, you'll want to carefully thread the end of that paper right through the little contacts on the spark generator. And finally, you'll clip the lead mass to the very bottom of the strip. It's that weight that's going to pull the paper all the way through. Okay, once it's all set up, just give it a quick look to make sure the paper is straight. And now for the big moment. You're going to press the switch, and this is key, hold it down. Pressing it does 2 things at once. It kills the magnet, releasing the mass, and it turns on the sparks. You've got to keep that button pressed until the whole thing has fallen through. That's how you get a complete set of dots. And just like that, you've done it. You should be holding a strip of paper with a nice little trail of dots on it. That right there, that's your raw data. Now let's figure out how to turn those dots into a number for gravity. Now, before we get into the math, we need to agree on one really important starting point. We're going to assume that we dropped the mass from a perfect standstill. In physics speak, we say its initial velocity, or v0, is 0. Trust me, this is going to make our lives so much easier. Okay, this equation here probably looks familiar from class. It's one of the big ones for motion with constant acceleration. It basically connects the distance something falls, that's y, with its starting speed, the time it's been falling, and the thing we're looking for, g. And this is why that assumption we just made is so awesome. Because we said the initial velocity is 0, that whole first part of the equation, the v0 times t part, just disappears. It goes to 0. And what we're left with is this beautiful, simple formula. From here, it's just a little bit of simple algebra to get what we want. First, we'll multiply both sides by 2. Then, we just divide both sides by t squared to get g all by itself. And there we have it. That's our golden ticket. G equals 2y divided by t squared. All we need now is a distance and a time. Okay, so we've got our formula. Now it's time to put it to the test. Let's walk through a sample calculation together so you'll feel totally confident when you start analyzing your own data strips.
All right, let's look at a real-world example. So on this sample strip, we measure the distance from the very first dot all the way down to the 19th dot. That comes out to 488 millimeters, which will convert to 0.488 meters. That's our y. Now for the time, well, that's 19 time intervals, and we know each one is a 60th of a second. So 19 times 1/60th gives us 0.317 seconds. We plug those two numbers into our formula, and bam, we get a g of 9.73 meters per second squared. Hey, that's really close.
And now it's your turn. You're going to run this experiment 5 separate times. Why 5? To make sure your results are solid. For each try, you'll measure the length, figure out the time by counting the marks, and calculate your g. And you'll keep track of everything right here in this data table. Once you've filled out your table and you have 5 different values for g, the next step is to find the average. It's super simple. Just add up all 5 of your results and then divide that total by 5. That number you get, that's your single best guess for g from this experiment. And for the grand finale, we're going to see just how good that guess is. You'll compare your average value to the officially accepted standard value for g, which is 9.81 meters per second squared. Calculating the percent error is the best way to see how close you actually got to the textbook answer. So let's just quickly recap the big ideas. We're here to find g, our local gravity. The whole trick is using that spark timer to get super precise time and distance measurements. The formula that does all the heavy lifting is g equals 2y over t squared. And finally, you wrap it all up by averaging your results and checking your accuracy with percent error. And that brings us to the final, most important question, the one you'll need to think about for your lab report. So, how'd you do? Was your result consistent with the known standard value? Think about all the little things that could have affected your measurement. How well did your experiment line up with the known value for gravity? Answering that is what this is all about. All right, good luck with your calculations.